Can I talk to you about your setup here?
Of course, yes.
Can I hand you the mic? You can hold it.
Oh, sure.
Yeah,
all right.
It's on and everything.
How's it going? Hello.
You're obviously with Berkeley.
Yes, UC Berkeley.
Is this a club that you're part of?
Yeah, so we're a student group at UC Berkeley. We're called Unmanned Aerial Vehicles at Berkeley. Yeah, we're a student group, mainly consisted of undergraduate engineers, mechies, EECs, CS, and yeah, we work on different components of the drone, and this year is our first year Berkeley is sending a competitive UAV team to SUAS, so we're really excited about that. That's in 1 week. Pray that we do as well.
So where is that at?
Yeah, that's going to be in Maryland, about an hour southeast of Washington, D.C., in one of the local airfields.
So what are the criteria for winning the race? Is it a race or is it, what is the criteria?
Yeah, so it's more like a robotics competition where it's mission-based. You get graded with points about how well your team, like how accurately it can go to the waypoints, how close it is to the target, although that's more of a binary thing. You have a target and you have to drop a payload from here within 20 feet of the target. If you do, then you get the points. And yeah, you have the waypoints, and of course you have to try. There's 5 that you have to drop. The more you drop, the more points you get. And yeah.
So for the waypoints, is that a programmed route, or are you driving it the whole way?
Yes, that's a great question.
Yeah.
So how the mission goes is that we take off, and then our drone needs to go to GPS waypoints that they give us, which may be like a loopy path around an airfield, and then we arrive at a zone where we need to start scanning the ground, and in that zone they're going to put targets. For instance, like targets that are a green hexagon with a red 3 in there, and the judges will say, hey, go to that target and drop something amongst maybe like a dozen or so. And when we do that, we drop it, we have to go through the waypoints again, go through the lap again, and then drop something else. The main point of that for the waypoints is just to artificially extend the path that our drone needs to take in order to drop something, to simulate something that a drone in the real world might encounter.
But you're not manually driving it, you're setting coordinates, or are you manually driving?
All autonomous, yes.
Oh, okay.
We pretty much press play, it'll go to the waypoints, and then automatically scan the ground for it, and then drop it.
And then modifying on the fly.
Yes.
Almost like with Google Maps where you'd add a stop.
Kind of, yes. Although all the stops are added at the beginning of the mission.
Okay. But what about when they say to do the drop? That's an ad though, right?
Sorry?
When they say to go to a target, that's a little bit of a tweak though, right?
Yes. So what we do is, it's not too bad. The code will say, hey, it detects something, it sends a signal to our onboard computer, which is not here because we're working on deving it. That gets sent to our flight controller, which then sends an electrical signal through the wires to a servo, which then actuates, a bar pulls across, and then the parachute deploys.
How are you identifying the objects that they're telling you to drop on? Is that almost like when you do a Google photo search, or how does it, when it's looking down, how does it know how to detect those things?
That's a great question. Essentially, it's using a machine learning algorithms. It's called computer vision.
Okay.
Essentially, it's a lot of matrix algebra. It looks at a lot of patterns. You give it a lot of data, and through those data sets, you can say, hey, we manually identify hey, this is an orange square with a letter in it. And you do that 100 times, those matrices will have numbers that then I'm not totally familiar with the math, but then it matches up so that once we feed a new information into these this matrix algebra, it's going to be able to say, hey, I identified this being closest to an orange hexagon with whatever number in it, and then
Does it remember that if it has to repeat that again?
Yes, it's all memorized, yes. We train it on the ground with these simulated things, and then it's loaded in a parameter set into the computer, after which you can start feeding in inputs, and it's going to give hopefully good outputs.
If you said find the basketball here, and then you flew, and it could find a basketball.
Yes. Wow. We would say we would give it. That's cool. We would go to Google Images, say, and get 100 images of different basketballs, and train it on it, and manually say, hey, see if it's successful in identifying it, or if it's not. If it isn't, we correct it and say, hey, that was actually a basketball and not a soccer ball. And then eventually you give it something new, so-called emergent data, and then you can properly identify it.
And was there a size sort of not restriction, but goal that you had to achieve with the size of it? Why is it this size?
Yeah, so this is all done through just physics and aerodynamics calculations. The basic question we had to first ask is how many rotors do we want to have? We could either have 4, like what's called a quadcopter, and that's the most common, have 6, or have 8, which is like a quadcopter, but you have 2 rotors on each of the 4 corners of, say, the square. And yeah, if we calculate the power, the efficiency, it turns out that a hex works the best for us. It can carry the most amount of payload and efficiently use power, and that's what we chose.
And then, what is it like? Is that carbon fiber? Is that what you use for the frame there, or what is that made out of?
Yes, exactly. This is layered carbon fiber. How they make this, we didn't make it, but we bought it.
Okay.
Essentially, they have like carbon fiber twill that's like weaved, and they have different layers of it, and they keep stacking it, and that is what's so-called impregnated with epoxy, which is like a liquid plastic, and that combination of this matrix, so-called matrix material, which is this epoxy, plus the fiber, makes something that's really strong, yet really lightweight. So that's why we chose it.
What about the poles? Are these the same?
Yeah, same thing. They essentially, instead of doing it in like a plate, you can wrap it around a cylindrical mold.
Oh, wow.
And so that's how you get that.
So there's nothing inside this?
Yeah, it's all hollow.
Wow.
You can see here, actually, this is the inner diameter and the outer diameter.
That's awesome.
It's a little thin for our liking, but that's just what we went with, and it's been okay so far.
And then, like, what's the range that you can go away from you?
Let's see. There's 2 different ranges. One is like the radio range. How far can it go before there's too much interference that we can't distinguish signal from background noise? That can go really far. That's like dozens of miles, I believe, in ideal conditions. But the main limiting factor for us is, of course, power. Let's see. Gets about 40 minutes of flight. It's about 5 miles of range. Oh, wait. Sorry, 12 miles of range, I believe. Okay. Yeah, 5 miles out, 5 miles back, and a bit of extra for emergencies.
And does this come back automatically if you have a problem?
Yes, it should be able to do something called return to home. What that means is that when it takes off, it records the GPS waypoints of where it took off, so it can come back. But if something goes wrong, we always have a safety pilot that's there controlling it, so if something does go awry, we can always take back control, but we get DQ'd if that happens, so we try to avoid it.
Okay, and what was the biggest challenge?
Biggest challenge? I think I know. Failures that we couldn't anticipate we couldn't anticipate beforehand, from like just engineering and doing like physics to try to solve how something behaves. I think the best example is like loose, just screws coming loose due to vibration.
Oh, wow.
You really can't predict that. We just have to know like, hey, which ones get the worst vibration, and just apply Loctite afterwards.
Was that happening during flight?
Yeah,
and what did it do?
So fortunately for us, it hasn't been. We have obviously a bunch of screws, so it's like redundant. But if a lot of them came loose, that would have meant we prevented rapid scheduled disassembly. But we always check, because this is such a prototypey thing. We always make sure to check it before every flight to make sure all the screws are tight.
How do you think you guys are gonna do, and what other colleges do you think are like the ones to beat? Like, or are you the one to beat?
I think it's definitely you don't really know how the other teams do, aside from 1 month before competition, all the teams submit a technical design review video where they talk about why they made what they did, and at the end of the video they have to prove to the judges that, hey, we actually flew for 12 miles and our drone is airworthy. But aside from that, you really don't know what their capabilities are, so it's really like trying to it's a race against yourself. But just because we know that, I think this puts so much strain on others teams as well. If we know that we can do a lot of mission demos at home, i.e. simulating what the competition circumstances are like successfully, then we have a pretty high chance of doing well. We're still in the process of testing more and more.
You feel like you have a chance at winning?
That's hard to say. The next, between now and June 25th, which is when the competition starts. We still have a lot of testing in the pipeline. Depending how that goes, we'll have a better idea. But the main thing is all the systems work except software, which takes a lot of debugging and effort, which we didn't foresee, which is, of course, a fantastic learning experience. But depending on how that goes and how many tests we can do to try to simulate as many failure cases as possible, that will determine it. Sorry, I don't have a good answer, but that's the best I can give.
And how much weight can this lift?
So technically, I think maybe
you tried to lift yourself?
Probably a small trial and maybe me, but that's if it's going at 100% throttle, which is not efficient. We try to hover at about 30 to 40% percent of like max power for efficiency.
And have you done anything sort of funny during your testing, like delivered a beer to your neighbor or something like that?
I wish, but the answer is absolutely not, because it's not safe. Just getting it off the ground is already terrifying, and we've spent like thousands and thousands of dollars and too many hours.
What was your name again?
Franklin.
Franklin. I'm Mac. I'll give you my card if you want to see our interview.
That'd be great. Yes, YouTube, great. Okay, thank you.
So thank you so much. We're live now.
Live. I
the
see
video
the
will
Twitch
be
stream.
after,
Okay, sounds good.
Thank you so much. Thanks for talking with us. All right. That was cool.